Hello and welcome to this lesson for Chemistry 20 in the acid-base unit. Now, the solutions acid-base unit for Chem 20 is actually 1 unit, but I split them up into 2 shorter units just to keep them a little shorter so they're not quite as much information. So this would be then the first lesson of the acid-base section of the unit. So what we're going to talk about today are some properties of acids and bases as well as some of the theories of acids and bases. So first of all, we're going to look at some observable properties, also known as empirical properties. So acids, bases, and neutral substances have properties that distinguish them and some that are the same. Now, it's important to note when you have a solution, it's going to fit into 3 categories. It's either going to be acidic, basic, or neutral. Okay? So if it's not an acid and it's not a base, it's neutral. So let's talk about those properties. Acids have a sour taste, bases have a bitter taste. Neutral substances can taste a variety of different ways, but if it's sour, it's very likely an acid, and if it's bitter, it's very likely a base. Acids and bases both conduct electricity. When we talk about the theories of the acids and bases today, we'll talk about why they conduct electricity. Neutral substances, it just depends on if they're an ionic compound or a molecular compound. Remember, ionic compounds conduct. If they're soluble, molecular compounds do not. Acids and bases can neutralize each other, which we'll look at later on in the unit. And then we also have indicators that we can use. The different indicators that we have are litmus paper, bromothymol blue, and phenolphthalein are some solution indicators that we'll spend more time talking about later on in the unit. But they're common solution indicators that get used to help test, again, if you have an acid base or a neutral substance. Now, litmus paper also can be used on neutral substances. And when you use litmus paper, it comes in 2 colors, blue and red. If both the blue and red are red after you dip them in the solution, it's acidic. If both the blue and red papers are blue, it's acidic. If the red litmus paper stays red and the blue litmus paper stays blue, then the solution is neutral. Okay, bromothymol blue in a neutral solution is a blue color. This is my neutral column here. Okay, in a neutral, it's actually a green color, but it usually starts out as a blue color. Can be green depending exactly on the pH that you're at. But in an acid, it is yellow. Okay, in a base, it would also be blue. So when you're using bromothymol blue, if it starts as a blue color and it stays a blue color, it doesn't necessarily mean it's a base because depending on the pH, neutral could also be blue. But if it's yellow, 100% it's an acid. Now, phenolphthalein is another common indicator we use that has a color, and in a neutral solution, it is colorless. It is also colorless in an acid, so when it's colorless, that doesn't necessarily mean it's an acid. It could also be neutral. However, we know for sure that it's not a base because a base turns it a bright pink color. It's actually really cool to see how the phenolphthalein turns a bright pink color in a base. Now, acids will react with metals to produce bubbles of hydrogen gas. So if I have a solution, I'm not sure if it's acidic, basic, or neutral, if I put some metal in it, it's like copper metal or magnesium or zinc, something like that, in that solution, if bubbles start generating of hydrogen gas, that means that it's an acid. Bases and neutral substances won't do that. Now, pH level, we're actually going to learn how to calculate pH in this unit. But for now, just know that when your pH is less than 7, it's an acid. When it's greater than 7, it's a base. And if it is exactly 7, it is neutral. And then some examples. So acids, you should be able to recognize, they usually start with hydrogen. Okay? They're hydrogen bonded to an anion. And they although are defined as being molecular, they ionize in water, as we learned in the solutions unit. So we treat them like they're ionic, a hydrogen ion bonded to an anion. Now, some acids, like organic acids, have the H at the end, like acetic acid, okay? So acetic acid, that's the H that makes it the H ion that's making it acidic, okay? Bases are ionic hydroxides, but there's some other compounds that can be bases as well, like ammonia. We're going to talk about that today, why that is. But otherwise, you're going to recognize a base as having the hydroxide ion in it. It's an ionic hydroxide. Okay? And therefore, if it's not an acid or a base, so if it doesn't start with hydrogen, if it doesn't end with hydroxide, or is ammonia, because that's kind of just an exception, then most likely your compound is neutral. And that can be, again, either ionic or molecular compounds that don't start with hydrogen or end with hydroxide. Okay? Now let's get into our theories of acids and bases. There's two theories we're going to talk about today. We're going to start with the original Arrhenius definition of acids and bases. So Svante Arrhenius proposed the theory on them, and he was studying how some solutions contain electrically charged particles when they're dissolved in a solution. And so what are these electrically charged particles? So he said an acid is a substance that when it is put in water, it's going to ionize. And again, we use the word ionize instead of dissociate because it's not starting as ions like an ionic compound does when it dissociates. Acids technically are molecular, but they do form ions when they are dissolved in water. They form specifically hydrogen ions. Okay, so that's the definition of an Arrhenius acid. It is a substance that splits into hydrogen ions in water. It increases the concentration of hydrogen ions in an aqueous solution because water, actually to a very small extent, will self-ionize. It will split into hydrogen ions and hydroxide ions to a very, very, very small extent. Now the concentration of these two ions are equal, which is why water is neutral. Okay, so it has some already acidic and basic ions, but in equal quantities, so they're neutral. So an acid is something that is going to increase the amount of hydrogen ions in the solution. A base is a substance that is ionic, an ionic hydroxide, that dissociates into hydroxide ions. Okay, so because it's ionic, it's already starting as ions, we just use the word dissociate to talk about how it splits into its ions. So an Arrhenius acid splits into hydrogen ions, and an Arrhenius base splits into hydroxide ions. Okay, so the concentration of the hydroxide ions would increase in an aqueous solution when you add a base to it. Now, this is good and all, and again, when we're talking about identifying an Arrhenius acid or an Arrhenius base, any acid can be classified as an Arrhenius acid. It's any hydrogen bonded to an anion. Okay? Again, it's technically molecular, but it acts ionic once it's put in water. Bases, Arrhenius bases, are ionic hydroxides. So again, that means I have a metal bonded to the hydroxide ion. So sodium hydroxide, for example, or calcium hydroxide. Any ionic hydroxide is considered an original Arrhenius base. Okay? We're going to talk about modified now. What makes something a modified Arrhenius acid and base? And actually, before I even do that, I want to give you guys an example of what's happening here. So an Arrhenius acid, let's say HCl, when I put it in water, now it's usually going to start as some molecular compound, solid, liquid, or gas. When I put it in water, it splits apart into hydrogen and chloride. Okay, it ionizes is the term we use, but it's creating hydrogen ions. So when you have an Arrhenius acid like HCl, you just split it into its ions. When you have an Arrhenius base, like let's say calcium hydroxide, you also are going to just split it into its ions. Remember to balance the ions. There's one calcium ion and two hydroxide ions. Okay, so again, the production of hydroxide ions makes it a base. The production of hydrogen ions makes it an acid. Now, how does the modified Arrhenius definition work? So the original is, again, just simply the splitting apart of the compounds into their ions. The modified reaction instead shows how a base can also be something that reacts with water. So it doesn't just split apart, but it actually reacts with water. So what has the ability to do this? When it's reacting with water, we call it, and this is another definition you learn in Chem 30, a proton acceptor. Now, what does that mean? A proton is the hydrogen ion, okay? So what's happening, let's say I have ammonia. Now ammonia is defined as a modified Arrhenius base. It's not an original Arrhenius base because it doesn't have hydroxide ions. However, when I put it in water, it's still going to generate hydroxide ions, but let me show you how. It does it by reacting with the water, okay? So it, as a proton acceptor, takes the hydrogen 1+ ion away from the water to leave water once it loses that as the hydroxide ion. So it takes the hydrogen away from water to leave water as hydroxide. Now the other ion that gets produced, the H bonds to the NH3, and this makes the ammonium ion. Now the hydrogen carries a 1+ charge with it. So while ammonia had no net charge, gaining the 1 hydrogen brings it up to a +1 charge. Every hydrogen that it gains increases the charge by 1 because it has a +1 that it carries with it. Now not only ammonia can do this, anions, so ammonia and anions have the ability to accept a proton or a hydrogen ion from water. So let's say you have the carbonate ion, CO3 2-, okay? If I put that in water, it is going to again take the hydrogen from the water or the proton from the water. When the water again loses that hydrogen, we are again left with hydroxide ions. Now the other ion that we have, CO3 had a 2- charge, and hydrogen plus is going to bond to it to make HCO3. Now the charge, like I said, whenever it gains a hydrogen, a 1+ comes with it. So the 1+ is going to balance with one of the negatives, because there's 2 negatives there, to leave us with a -1 charge. Okay, so every hydrogen you get brings the charge up. Think of it along a number line, brings it up by 1. Okay, so a modified Arrhenius base identified as either ammonia or anions. Anions, remember, again, meaning any negative ion. So if I were to give you an ionic compound like, what's a good idea? Sodium phosphate. And I were to ask you, how is sodium phosphate, and it would be slightly basic. Arrhenius bases, the modified ones, are only weak bases, so they're only slightly basic. So how can this act as a slightly basic compound? Well, when I put it in water, first it's going to ionize into sodium ions and phosphate ions. Now the sodium ions are nothing, right? But the phosphate ions are an anion. So now I can show that those phosphate ions will, again, react with water. Notice how I'm writing water as HOH. That's just another way to write it to make it easier to see how that 1 hydrogen is leaving the water and bonding to the base. Okay, so I am again producing a hydroxide ion, and when the H bonds to the PO4, it will be HPO4. The charge was -3, so it goes up by 1 to -2. Okay? So, modified Arrhenius bases produce hydroxide ions again like an original Arrhenius base, but they do so by reacting with water. Okay, that's the key thing. They are reacting with water to take a hydrogen away from water, leaving water as a hydroxide ion. So again, if you're asked to identify a modified Arrhenius base, it would be either ammonia or an anion, a negatively charged ion. Okay? Now, what is the modified definition of an acid? So before we said acids ionize to produce hydrogen ions. That's the original Arrhenius definition. But scientists have studied that hydrogen ions do not exist in isolation because they are, again, an exposed proton, technically. Because they are, if you look at the subatomic breakup of a hydrogen, it has one proton, no neutrons, and one electron. When it forms the hydrogen ion, it loses that one electron. So it essentially becomes an exposed proton. That's why we call it a proton, because all it's made up of is one proton. Okay? No electrons, no neutrons, just a proton. So it is not going to exist by itself. It gets attracted to the negative poles of the water molecules that it's dissolved in, because again, these are solutions. This forms something called the hydronium ion. So instead of water being H2O, this is H3O, and it has a 1+ charge. This is called the hydronium ion. Okay? Now, all acids are going to do this, whereas the modified bases are only ammonia and anions. Modified acids are all acids. Okay? So all acids always react with water to produce the hydronium ions. So how I show this, rather than just splitting it apart, I add it to water, and what's happening, rather than accepting a hydrogen from water, a modified Arrhenius acid is what we call a proton donor. Proton, again, being the hydrogen ion. It gives the hydrogen ion to the water rather than taking it away. Okay? So when the hydrogen ion bonds to the water, that generates your hydronium ions, the acidic ions in your solution, the hydronium ions. And now, when my H is gone, I'm left with a chloride ion by itself. Okay? So again, acids donate or give their hydrogen to water, a modified Arrhenius acid, and produce hydronium. Okay? So here's a summary. The original Arrhenius acids, they just split apart or ionize into hydrogen ions. The original Arrhenius base are only for ionic hydroxides. They split apart into hydroxide ions. They just dissociate into hydroxide ions, okay? So just the straight splitting apart into ions is the original Arrhenius acid and base definition. But the modified Arrhenius definitions is how they react with water. Okay, that's the key thing, is they don't just split apart, they actually react with the water. So a modified Arrhenius acid produces hydronium ions by donating the hydrogen to the water, and the modified Arrhenius base produces hydroxide ions by accepting the hydrogen from water, leaving water as hydroxide. Okay? Again, for original Arrhenius bases, they are always ionic hydroxides. For modified Arrhenius bases, they are ammonia or anions. Okay? The Arrhenius acid and modified Arrhenius acid, we always go with the modified Arrhenius acid method for acids. We always react them with water to produce hydronium. So it's basically like saying the original Arrhenius definition of an acid is not complete. It's not accurate. It's more accurate to use the modified Arrhenius acid definition, because acids always react with the water they're dissolved in to produce hydronium. Okay? Whereas bases, if it's an ionic hydroxide, it'll follow the original Arrhenius base definition, but if it's ammonia or an anion, it'll follow the modified Arrhenius base definition. Okay? So I hope that makes sense. There's a few definitions and understanding what's happening. But this again is kind of your introduction into acids and bases so that you have a greater understanding once we start getting into some of our pH and pOH calculations. Thank you very much for watching.